Hello students, this is Dr. Diaz and I'm here to practice a little bit more about how to determine the SN1E1, SN2, and E2 reactions. So I have here some few examples and let's practice a little bit together today. So remember that I said during class and you saw in the videos and also in the book that heat will always favor eliminations, right? So, and the fourth, like we have methyl, we have primary carbon, we have secondary carbon or tertiary carbon. Remember that SN1 form carbocation, right? So if you form a carbocation, we need stability. And one thing that will tell you that we will not have SN1 is the if the carbon is primary, secondary, tertiary. We know the method will never happen, and the primary carbon also will never happen for SN1 because carbocation will be very unstable. Remember, if you have a tertiary carbon, imagine if you have like CH3 here and CH3 here and CH3 here and the halides over here. So when this leave, what you're gonna have is a tertiary carbon. We put R instead the methyl over here. So then we're gonna have a more stable carbocation because the neighbor, remember when we have neighbors, these neighbors will help to stabilize this positive charge over here. So in this case, we have, look at me, this, we're gonna have 1, 2, 3. This is a tertiary carbon, right? Tertiary carbon. So SN2 will never happen with tertiary carbon. Okay, if you have a tertiary carbon, we will not have SN2. And why? Because SN2 is a concert reaction. Remember, concert mechanism. So everything happens at the same time. So if you have, imagine I have here my nucleophile over here attacking in the back because it's always in the back side, 180 degrees from the leaving group. I will write here leaving group. If you have a lot of substituents over here, like no hydrogens, less hydrogen is bad. This will not happen because this will not allow the attack of nucleophile here. So this will not happen. So if you increase the size of the groups around the carbon that is hold the leaving group, we reduce the nucleophilicity over here because the nucleophile will not be able to attack on the backside of this molecule. So this tertiary carbon, so that means I cannot have SN2, but I can have SN1, right? But since I have heat over here, and also another thing that I tell me is this can be SN1 is this weak nucleophile or base. Okay, so that we have a weak base over here. So since I have heat, this will not be SN1, will be E1 over here. And this will leave, this leaving group, and we're gonna have here a carbocation, tertiary carbon. And then, of course, we have hydrogens over here, and we have another hydrogen over here. So the base will attack this, or the base can attack this. So we extract the proton, okay? And the proton will always leave behind the electrons. So it can be this position or this position to attack. You remember, SN1 and E1, we can attack in every side, like in the back or in the front. And here we're gonna produce this, and the second one that I showed you over here. This we can call Zaitsev product, because the other one, because I have 1, 2, 3 substitution over here, the other one, this attack over here will produce this over here, this product that we call Hoffman, right? And this is the Zaitsev. Okay, so this will be the major, right? Because this is more stable. And this is, that is E1. It's a weak base over here. So of course we can have both product, but this is the major Zaitsev. More substitutions here. In this case, I have only 1, 2 substitutions over here. Okay, let's go to the second one. So the second one here, we have heat as well. And here we have a secondary carbon. We have heat. So we know that will provide elimination. Up to now, if you look at its secondary carbon, it could be, okay, it could be SN2 or SN1 because they are good for both, right? So, but now I have heat, so it will be elimination. But when I look to my nucleophile base over here, this is a strong base, right? So I have a strong base. So what's gonna happen here, this will favor elimination 2. If it was a weak base, will favor elimination 1. So here we're gonna have elimination 2. And we know that elimination 2, like this SN2, is a concerted mechanism, so everything will happen at the same time. So we don't have a carbon cutting over here. We have this hydrogen over here. So the proton will, that the base will attack is always in an adjacent carbon. So beta carbon here and beta carbon over here. This beta carbon is the neighbor of the carbon that is carrying the halide group or the positive charge that is going to be here. So that's the alpha. So now, so the base can attack over here, or the base can attack over here. And this proton will leave behind the electrons. And we're gonna have, let me draw again. I start bad. We're gonna have this product over here. And we're gonna have, again, this product over here, right? So, but since we have a small base, we're gonna have here Zaitsev. But pay attention, if you have a book base over here, let me just move this down over here. So if you had a book base, so instead we have this, imagine if I have a book base, like here. This is a book base, butoxide, right? And heat. So what you're gonna have, let me put this down again. I need more space. So this is a bulk base. So the nucleophilicity also reduced over here. It's a strong base, but will favor Hoffman product because since it's a bulk base, this will be easier to attack this proton over here because we have hydrogens around than this one that we have another groups around. So that will be easier and the less energy is spent if you attack this proton over here. So what you're gonna have will be this product. We're gonna have both, but Hoffman will be the major, okay? As you could see in my video. So this is those over here. So this will be the major here. If you have a small base, Zaitsev will be the major. So pay attention to that, okay? So let's go to those two over here. So small here. So what do we have here? First thing I'm gonna do is look into my leaving group. So my leaving group over here is this, right? So this is my leaving group over here. And this is a good or bad leaving group. It's a good, right? It's a good leaving group. We have a resonance that helps to stabilize the negative charge. So it's a good leaving group. And we have here a secondary carbon. secondary carbon, I could have SN2 or I could have SN1. And but look at this solvent over here. What do we have here? DMF. So we have a good living group. We have this strong nucleophile because we have this, right? Negative charge, strong nucleophile. So let me strong nucleophile. And we have a DMF, which is polar A product solvent. So that's it. So SN1 will not happen, but we can have SN2. Yes, we have everything that tells us this will be SN2, polar A product solvent, strong nucleophile, and a good leaving group. So everything will happen at the same time. So we have the attack on the backside. So the attack on the backside, right? Over here, so you can draw then the transitional states, but don't ever forget to write down the parentheses over here, so you know that the nucleophile will attack in the back. So then we're gonna have the carbon. I will call this R. Okay, so R over here, and they have our leaving group. So I will put here the hydrogens over here, and this methyl group over here. And we have this dot lines over here that shows that everything is happening at the same time, and so it's forming a new bond and it's breaking the bond with the leaving group. Everything is happening at the same time. So we have a partial negative charge here, partial negative charge over here, right? So our final product will be this. Don't forget that SN2, we have an inversion of the conformation, right? Let me just draw this again. This is ugly. I'm not good in draw today. I don't know what happened to me. It was better before. So what we're gonna have here is this one. So we're gonna have OH over here. So now, before we have the methyl group here, so the hydrogen will be behind. So now what we have is the hydrogen will be in the front, and now this methyl group will be behind. Okay, so that is inversion of conformation. The other one will be the last one. So what are we gonna have here? Tell me. What do we have here? So we have a chlorine, we have a book base. So what do you, so let me just grab my, another color here. So not to get confused. Okay, so I have primary carbon. So I know that SN1 cannot happen. I have, so my option will be SN2, but I know that I have a book base. So book base, it's a strong base, but it cannot be SN2, so will be elimination 2, right? So everything will happen at the same time, so this will leave, and then the hydrogens from here can be extracted by the base, and this will leave behind this product. These electrons over here forming the bond. So this is my final product over here. So this is a way that we should analyze the reactions to see if you have the solvent, if it's a polar A product or polar product. So we know the A product will always favor SN2. Stronger nucleophile will favor SN2. Secondary carbon, we can have SN2 and SN1. If you have heat, we always favor eliminations. if you have a good nucleophile, a good living group, a strong base, but it's a book base, so that will be elimination, not as a substitution. Okay, that's it. That's all.